Okay, good evening to everybody. It's evening, I think, in the time zone of all the people who have come today, and belated Merry Christmas to all of you, and also uh, best wishes for the upcoming New Year. So today is the 8th lecture, and I think we have been making quite decent progress. So we have almost reached the quantum theory. I think I will start the discussion of the quantization procedure today. So my goal is that by the end of the next lecture, I should be able to give you a decent idea of what spin networks are and what the state space, the quantum state space of loop quantum gravity looks like. And then in the 10th lecture, I can talk to you about one of the most important applications of that state space, which is the counting of microstates of black holes. And then I can have a few more lectures after that, depending on your interest, where I talk about some other aspects which are not necessarily, what would I say, conventional in the LQG community. So, but would involve more of my own personal prejudices and preferences. Okay. All right. So now, questions about what we have discussed so far. So I'll just briefly go over the last lecture. If you have any questions, please ask. Okay. So what I have shown is that you can write down this Einstein-Hilbert action using in a first order form using a tetrad and gauge connection, which is a SL2C gauge connection, and the relationship between the Riemann tensor of the usual metric formalism and the field strength curvature of the gauge connection is given by this expression. So the tetrad sort of mediates. That's why it's called the soldering form. It mediates the relation, the gauge field and the metric curvature. So in this form, this is, you can call this connection gravity. It is completely equivalent to Einstein gravity. And if you solve the equations of motion, you find that the equations of motion give you precisely the same results as Einstein-Hilbert action, which is that in vacuum, for instance, you would get that the Einstein tensor would vanish. Then regarding the Hamiltonian decomposition of this theory, I skipped over the details, and I just went to the sort of the definition of the constraints in terms of triads. So the triad is now when you restrict to the three-dimensional spatial slices, right? You will have three legs, triads, and your connection becomes an SU2 connection rather than an SL2C connection, and your phase space variables are determined in terms of so there is one of the variables is this extrinsic curvature 1 form, and this has to obey the requirement that the extrinsic curvature tensor KAB is symmetric, right? And so this fact has to be reflected upon the structure of the curvature 1 form. And this is done by imposing a certain constraint, which is that the antisymmetric part is 0, which can be written as in this way as a constraint on this one form. This constraint can be written as GAB is equal to 0, and it becomes what is known as a Gauss constraint. Then for the other phase space coordinate, we introduce these densitized co-triads, and you can think of them as either as one forms or as two forms, because you have in 3 dimensions the duality between one forms and two forms, right? And then one can write down the Gauss constraint in terms of these densitized triads, and you can also translate your Hamiltonian and diffeomorphism constraints into these variables. So in the metric formalism, you have this metric HAB. It can be written in terms of the densitized triads. The only new thing here is that there is a determinant factor that appears. Then in the ADM version, you have a momentum, which is related to the extrinsic curvature and the metric tensor. And this is given by this, when you translate it, you get a certain expression, right, which involves both the triad and the extrinsic curvature. And then you can write down the diffeomorphism constraint and the Hamiltonian constraint. Now, and then I talked about, well, the action of these constraints and the fact that they generate diffeomorphisms as we expect. So finally, in terms of connection variables, we have this summary that if you look at the Hamiltonian constraint, it looks like this, and the connection, the momentum constraint looks like this. Now, again, this is not very particularly enlightening. So we introduce we perform a coordinate transform to these Ashtekar variables. And it involves the introduction of this new connection, which is a shifted form of this Ki. Now, right now, here, when we are working with these co-triads and this extrinsic curvature, neither one is the extrinsic curvature one form is not a connection, right? It doesn't have that property of transforming as a connection under local SU2 gauge transformations. So we introduce this coordinate A, which is given by this expression. Now, this involves this gamma. Now, what is gamma? Gamma is the Christoffel symbol defined on the spatial manifold, and it is a Christoffel symbol which is compatible with the 3-dimensional metric on that manifold. And so this connection, the Ashtekar connection, is a linear combination of this Christoffel one form and the extrinsic curvature one form. And also one important fact is that there is a factor of I. So this is a complex connection. Okay, this is an important point which becomes which is we have to be careful about. So finally, we are left with the following framework. We have a tetrad and a connection on space-time, and when we reduce it all down, so instead of omega, instead of omega, I should write this as AIG, right? This is the Ashtekar connection. And no, I'm sorry, my mistake. I was explaining the relationship between where this Christoffel connection comes from, or not really the Christoffel connection, it's actually the spin connection, and restricted is the pullback of the spin connection to the spatial manifold. So in terms of these variables, the Gauss constraint, for example, the Gauss constraint can be written in a form which actually resembles what we normally think of as the Gauss constraint, which is that the derivative, the divergence of this, the triad vanishes, and or the divergence of the co-triad vanishes. And this actually is a Gauss constraint, right? Because it implies that if you take the flux of the co-triad through some closed surface, you have some closed surface, and NA is the unit vector on the closed surface. Tau I are the SU2 generators, and you take this integral, which is a surface integral, then the Gauss constraint tells you that this is 0. So the flux of this quantity through any closed surface is 0, right? Because there is the right-hand side is 0. There are no charges which would source this electric field, so to speak. So in these Ashtekar variables, this is the final form of our constraints. And in particular, the Hamiltonian constraint now has a very simple form. It is quadratic in both the connection and in the co-triad. And so this is where we had stopped last time. Now, are there any questions at this point? Okay.
Can you remind me again? What is co-triad?
What is the co-triad? Okay, so the co-triad. So you have the triad, right, which is this guy related, and this is a SU2 valued one form, right? So this is a spatial index. A is equal to 1, 2, 3, which takes values in the spacetime manifold. This is an SU2 Lie algebra index. Okay, so you can construct the 3 metric by taking the inner product of these vectors on the internal space, right? In the same way that you could construct the 4 metric by taking this inner product of the tetrad. So in terms of this triad, we now define our this object as 1/2 epsilon ABC epsilon ijk EBJ ECK. So essentially what you're doing is you're taking the cross product of these vectors, right? So as I illustrated in a picture here. So imagine that you have 3 of these triads, right? So you can write this corresponds to 3 vectors, right? And you can think of these as spatial vectors for the simple reason that the SU2 indices, SU2 can be mapped to a vector, right? If you have any element of SU, any Lie algebra element of SU2, that can be mapped to a 3-dimensional vector by contraction with the Pauli matrices. Okay.
Yep.
Is that fine?
So the co-triad and the delta is a triad, is the same thing.
So well, I mean, if I take the inverse of this, then I would call this the co-triad. But I'm, so but this thing is it is a density weight 1, I think. So when you transform it, you get a factor of the determinant of this of the metric, which is just the square of the determinant of E. So this is a densitized object. That's why we call it a densitized cotriad. And it's a cotriad because, well, the spatial index is contravariant.
Okay. I got
Right?
it.
Yeah. So okay. So now we have these constraints. And in terms of these constraints, the question is, can we use these constraints to do something useful with general relativity? So one of the things that we can do is we can use these to write down an exact solution of the Hamiltonian constraint. And this exact solution is something. Yeah, Mustafa, you can just ask. Go ahead.
Is the Gauss constraint first class with the other two, the Hamiltonian and the Diffie?
Yeah, I believe on shell there are. Yes.
Okay, thank you.
Yeah. Now, at least in the Ashtekar variable, I think when you go to the real variable, so there's a different set of variables that one can use, called the Ashtekar-Barbero connection. There you do get some second-class constraints, but again, those can be dealt with. So I won't go into details of all of that. Okay.
Okay.
Now, right. So we have one of the prototypical gauge theories is that of the Chern-Simons theory. So Chern-Simons theory is a theory of a well, connection can be non-abelian also. It doesn't have to be. It can be abelian also. It doesn't have to be non-abelian. But we're going to talk about the non-abelian case. So this is a theory which is where again you have I is some Lie algebra index, A is your space-time index, and in terms of this you define your Lagrangian as A wedge dA plus 2. And if you want to write down all the indices explicitly, you would write it as A, B, C, Ij, anti-symmetrized over ABC, or if you prefer, you can put a factor of epsilon ABC. That's what I'll do. And then for this ijk, you can put a delta ij contraction, 2/3, then again AA, ABJ, ACK, and then here you have to put an epsilon ijk and put an epsilon. So this is the right. This is a very famous action. It was made famous by, in particular, by, for example, Witten, right? When he talked about knot theory and the Jones polynomial, right? So what he showed was that if you look at the partition function of this Chern-Simons theory and evaluated on an arbitrary knotted configuration, a knotted word line of a particle. So this is in 2 plus 1 dimensional theory. The result is the same as something called the a knot invariant, which is called the Jones polynomial. Right. So this was one of, it was important because it showed that there is a close relationship between knot theory and gauge theories. And this also indirectly have some influence on the development of LQG, right? Because the way LQG developed was initially there was this the state space was written in terms of holonomies, and the spin network picture came a little bit later. And when you write it in terms of holonomies, you basically have this knot algebra, because you have to talk about your variables are defined along closed loops. So you have to talk about how these loops can be combined with each other and what happens when these loops intersect. And so the result is that you get a certain algebra that is you're talking about knotting and unknotting, right? So if you look at this Chern-Simons action, so the associated Chern-Simons action,
I have a question,
would
Tiboga.
be something like k by, yeah, sure.
Just being a curious, what meaning of knot theory, or what is the role of the knot theory in physics? In the sense, in particle physics or in physical world, how they are how they carry significance.
Well, I mean, knots are important because they correspond to non-trivial topological configurations of gauge fields.
Okay.
So you can have these knotted configurations in electromagnetic theory also, and also in Young-Mills theory. That's one thing. Then, of course, there is the very old attempt by Lord Kelvin and to think of elementary particles as knots in the ether, right? And now, in many ways, we have come back to that picture again, because if you think about, for instance, what string theory tries to do, right? String theory, you have the compactification of your string. So you have the 6 or 7 dimensional manifolds, which are called these Calabi-Yau manifolds. And so these are more complicated than just knots of one-dimensional loops. But the point comes, it's the same sort of notion that you have some sort of irreducible geometric objects, right, and which constitute the basic atoms or elements of your space-time or your reality, or whatever you call it. So knot theory is important at many different levels. It's important in turbulence also, in hydrodynamics. Okay. So the Chern-Simons action looks like this: d cubed x, and then you have this Chern-Simons term. So now, if we perform a variation of this, right? So it only depends on the connection, right? And if you perform a variation, what we will find is, so if you look at the first term, so let me call this L1, let me call this L2, and again I'll be schematic about it. Okay, so if I look at the variation of the first term of this Lagrangian density, what you will see that, well, you will get a term of this form times delta Aij, right? And then you can do an integration by parts and write down again, the expression for the perturbation of the second term, right? So you can write that as something dBAi Cj delta Ij, then minus. So you will get the same term basically. Okay, you won't get anything new. Then so we'll just call this a boundary term. Put it delta here, and then if you look at the second term in the Chern-Simons action, the Lagrangian density, you see that, well, you have a factor of 2 by 3, and what you will get is something like ABJ ACK epsilon IJK epsilon ABC. Okay, and you'll get three such terms because you have three, so you'll get, you know, three will cancel out, and then the factor of 2 also goes away. So ultimately, when you combine delta L1 plus delta L2, what you get looks like this, something like DBACJ plus AB. If I want to write down the indices, if I want to be careful with the indices, AB, CK, epsilon IJK, epsilon ABC, delta A. So this is BC, delta A, and then which index is missing? I, right? I, 1 second. Okay, delta A, then I have to put some index. I'll put it here, delta J. Then I have to change some of the index somewhere. Okay, well, again, I won't worry too much about all of that. But the main thing is that if you look at this expression, and there's anti-symmetrization over these A's, well, this expression is nothing more than the curvature of this connection. All right, so the curvature has this form, right? If you write it as a differential form, it looks like this, right? Where this is the exterior derivative, right? And this is the A wedge A. So that is exactly the expression that you get when you perform a variation of this Chern-Simons Lagrangian density. So you get FA, and then this FA will have some indices, let's say AB, and it will have one Lie algebra index, and you'll get something like this, delta ACJ, delta I. This is what you get when you perform the variation of this Lagrangian density, right? So now if I write down an expression of this form, let's say psi A, which is exponent of some minus I, and then S Chern-Simons. And then I ask, well, what happens if I take the functional derivative of this with respect to the gauge connection AI, right? So you can write that as this minus I delta times psi of A, right? This is how you would take the functional derivative, right? You just bring the exponent down and take it the derivative. And this quantity, we know what this quantity is. This quantity will be something that is proportional to, so BC, again, to match, get the indices, let's say J, and then epsilon ABC, something like that. Yeah, you would get epsilon and then this, yeah, that's minus I times psi of A. Okay. And so we have this form of the Hamiltonian constraint. It contains two of these co-triads, and it contains this curvature tensor. So if I write this as an operator, okay, and again, you know, with the naive quantization that my connection goes over into an operator whose action on this is, just like the quote unquote position operator. And then I say that my momentum operator, so something like this goes to, so I'll just put a tilde in a caret, which can be written as something like minus IH bar del by del. So this is quote unquote momentum, and this should act on psi of A and psi of A. Okay. Right. So this is just a naive thing that one can do, and then your Hamiltonian, you can write down an operator version, which looks like this: epsilon ijk, then fk ab, and then you get minus minus something minus h bar square del ai del a bj. Okay. And now you ask, well, what sort of functionals of the connection would satisfy this constraint as an operator equation, right? So if you have that your psi of A is equal to the Kodama state, that's what this functional is called, this thing, okay? And this is not a, this is well known in gauge theory also, this sort of a functional, okay? So it's not very surprising that it solves this constraint. And then you take the variation, you get you get 0, right? So this is solved by this functional. Now, right. So one factor of delta will bring down this thing. When one factor of delta acts on this this derivative, you will get one copy of f, and then you will have another delta acting on it, but then that delta will act on f multiplied by the state. So when you apply the Leibniz rule to both of those, you will see that the terms will cancel out and you will get 0. Okay. Naively, of course, if you just do it blindly, then you would think that, okay, well, this will just give me 2 copies of the curvature tensor, and then, well, that's obviously not going to give me 0. But you have to be careful because this is a derivative acting on whatever it is. So h acting on psi of A would be something. I don't know why they put a minus sign. Yes, the minus sign is because of the I. So f a b k s squared delta by delta I a b j. Okay. So you have to take the derivative of this with respect to A, and then the derivative of this whole thing with respect to A. And this gives you 0. Okay. So this is an exact solution, and one is nice because, well, you never had such a possibility with the metric formalism, right? And now maybe one can proceed and try to ask more interesting questions. Can you construct a cosmology out of these states, and so on and so forth? So if you are interested, you can look at some papers, the original paper by Kodama, then work by Chopin Su, and also by Smolin. And then more recent, well, by recent I mean like 10 years, more than 10 years ago, work by Randono. All of this work. So there were some issues with with the inner product on this, on the set of states of these Kodama states. But Randono eventually resolved all of those. Anyways, so this is, if you're interested, further reading. Okay, and I think the Kodama state is still, important. We just have not exploited it properly. That's one reason why I'm taking the time to talk about it here. Okay, so now this is one way to quantize, right? So one way to quantize, for instance, if you have a scalar field, right? What do you say? You say, well, your field becomes an operator, or an operator value distribution, or some jargon like that, right? And same thing with your momenta. And then what you do is you say that, well, if I want to write down commutators of these fields, I smear them with some functions, and on my whatever my background manifold is, and then I do something like this, prime, so on, and then this gives me a delta function. But this delta function, again, there are issues with all of these definitions, right? The one main issue is that these are volume integrals, right? So if you look at this whole the Poisson object, right, this combined integral, it's a 6-dimensional integral, right? So when you do, I mean, you can perform some of those integrals using delta functions, but you are still left with some volume term over here, something that is proportional to the volume over which you are integrating. Okay, and so the similar technique is applied for the quantization of symmetric. You take your you take these to be some operators, you impose your commutation relation. Again, the commutation relation has to be suitably smeared. I'm not doing all of that. So on. Right? Yeah, Devamalya, your question?
In the commutator of fx, phi x, and g prime, pi x prime, the integrations are taken over the x and x prime, right? And it is volume integration. So how
right.
the
this is
contains Dirac delta function?
Sorry?
How the right hand side contains the Dirac delta function of x and x prime, because already the x and x primes are integrated out or integrated over in the left hand side.
Right. I guess it won't. Well, so okay. Well, I don't know. It'll give you something. You can work out the exact expression. You start with this phi of x, and then phi of x prime, and you say that this is equal to h bar delta x minus x prime. Then you can work it out and see what you get. Okay. So I'll leave that to you. You'll get something like integral d cubed x fx gx, something like that, right? Quantities you'll get. Right. There's a better way to do quantization when you're working with the connection variable. With these old variables, you don't have much of a choice in how to do the quantization. Right? These are tensors. If you want to smear them, you have to contract them with other tensors, and then you have to integrate the whole thing over your spatial volume. But now, if you are working with your connection variables, so you have this gauge connection and this co-triad, and now you have a new possibility that opens up, a new way to construct the quantum theory, right? Which is that you can construct, you can take these quantities and integrate them along one-dimensional lines or along two-dimensional surfaces. So, for instance, the connection, this is a one form. So, rather than smearing it, rather than treating it as a three-dimensional field, you can treat it as something that is smeared along a one-dimensional loop. So you can take any path in space, say gamma, and with this gamma you can associate ds is the line element, then aai x is just the coordinate along the path times this Lie algebra, and then there will be, let's say, na is the tangent vector to the path at each point, right? So you can smear your variables in this way for your gauge connection, and this tetrad is a two form. Your triad, right? Because you remember that we have this epsilon ABC, right, which we are multiplying to write it as one index. If you remove that epsilon ABC, we are just left with something with two indices, right? So it's actually a two form in disguise, right? So it makes sense to define an integral over surfaces. So you have some surface, okay, and you take the flux of this quantity, okay, through the surface. So you integrate it, you multiply it by the unit normal. This is the unit normal to the surface, defined at each point on the surface, right? So this is you're integrating the two form over the two-dimensional surface. This is the same thing, right? So you can call this the flux of this quantity through the surface S. Okay. Now, so if you use these as your basic smeared objects, right? And then in that case, when you calculate your Poisson brackets, for instance, so let me call this something like f lambda a, and let me call this GSE, f lambda a and GSE, Now the nice thing is that this is a one-dimensional integral. This is a two-dimensional integral. So in this Poisson bracket, right, the whole thing becomes a three-dimensional integral. And you don't have any regularization issues which arise due to the presence of this integration over the spatial volume in the case of the regular quantization procedure. Okay. So this and this has the following form. If you ask what is the commutator of these operators or these observables, you get something which is zero. So I will just define it geometrically. If so, you have some surface S, right, with respect to which this G is defined, and then you have some path gamma on which A is defined. Now, unless there is some intersection between gamma and S, unless you have some intersection between these two, your commutator will be zero, right? For the simple reason that, for example, if you look at this commutator, if F and G, they have support on disjoint regions of space, then this commutator would be zero, right? So for the same reason, right, if your gamma, your path gamma and your surface S, they have no intersection, this will be zero. There is no intersection. I'm really squeezing that in. And otherwise, if there is an intersection, then your commutator will it will not be zero. It will depend on how many times your path intersects. So it will depend on the number of intersections between your path and the surface. So for instance, your path could come around like this, and you could have multiple intersections of the path of the surface and so on. So, and then of course there is a possible degenerate case when the path, this one-dimensional path gamma, this lies within the surface. So in that case also one can show that this is zero. Okay. So you can, yeah. Now, so this will be the strategy to proceed with the quantization. Okay. We will be working with objects that are smeared along one-dimensional lines and along two-dimensional surfaces. And this is up till this point, see, we have not done anything which one cannot do in any gauge theory, whether it is Maxwell theory or whether it's Young-Mills theory, right? So this kind of a quantization procedure, right, we'll call it loop quantization. For the reason that originally they defined these observables for closed loops, where so T gamma was this integral along a closed loop of this connection, I x tau I, and then you had some sort of commutator algebra of the variables defined on different loops, and the commutator algebra was non-zero if the loops linked with each other and so on. So it became, but so it was very complicated, this loop algebra, right? So now nobody looks at that. Okay, because you work with this, with these spin networks, and in the spin networks, things are much more simple. But the spin networks remain a faithful representation of this loop algebra. Okay, so if you are interested, one can also look at work that is done, I think, among others, by Vicar. Let me check to make sure that I'm not saying anything wrong. A second. Loop quantization of sorry, not Vicar, but by Madhavan Vardarajan, right? So if you are interested, one can look at that. Maxwell theory in the loop representation, right? So the paper is Fock representations. So basically, one can ask this question, right? That when you do the quantization of the electromagnetic field, you get this Fock space of harmonic oscillators. And the natural question is, can you relate the quantization done using these loop variables, and can you reconstruct? Is it equivalent to doing the usual quantization of the electromagnetic field? And the answer is yes. Right? So this is what the work by Vardarajan back from 2000, and it's still quite instructive to refer to these papers. There is Maxwell theory in the loop representation. So more precisely, Fock space. That's the title. Let me write it down. Fock representations from U1 holonomy L. Okay, and this paper is also quite readable, so that's one other reason I'm mentioning it. So shows the equivalence of the Fock space of quantum Maxwell theory and the loop state space. Okay, so this is important, right? I mean, this is non-trivial, and one has every right to ask whether this quantization procedure agrees with what you already know. Because if it doesn't, well, then you should have to ask yourself, why does it not agree, right? I mean, you can't just make up something new just for the sake of novelty. You have it, I mean, that's one of the things that makes research such a frustrating endeavor, right? Because you can't just make things up for the sake of novelty. So, unless you're a string theorist, okay, that was just my, cheap humor at the expense of string theorists. I deeply respect string theorists and string theory and the work they have done for the advancement of science. Okay, that was another cheap. Okay. All right. But of course, Adi, from those, if you have watched these lectures and my papers and all, those who have, are familiar with my work will know that all jokes aside, I think that a successful theory of quantum gravity has to combine elements of both string theory and LQG. Okay, so now the question is, well, how do we construct our operators and so on and so forth? Okay.
Deepak,
Yeah.
can I ask you a question?
Yes.
I think I missed what is a Poisson bracket of a tetrad and the connection when the curve is on the plane.
Oh, you mean, okay, in the degenerate case, right? So that's the degenerate case when the curve lies on the plane. So in that case, the Poisson bracket vanishes.
Vanishes.
So unless there is an intersection, that is, unless there is a component of the curve which is normal to the surface at some point, right? Unless there is some normal component, the Poisson bracket will be 0.
So, well, for example, when the curve gamma is really when you consider a limit of gamma really parallel to S, but not exactly parallel to S, then Poisson bracket doesn't vanish.
Well, I mean, if you consider the limit and when it is parallel but not exactly parallel, right? I mean, the Poisson bracket would be right. It would not vanish, but so you're saying that there is a discontinuous
yeah, right,
change
right.
in that? Is that what you're saying?
Right.
Okay, let me try to be a little bit more precise if I can. 1 second. Again, I have to open up the reference for that. Second. One second. I'm trying to confirm or deny whether I'm saying is true. So I think, yeah, there is this there is a sort of a discontinuity there, but I don't think that it is unreasonable, because when you think about it, in the quantum theory, what happens is that these punctures they become the punctures can be associated with quanta of area. Okay, so to answer your question as to whether there is, so this is a very nice question. So let me just try to answer it in a sort of an intuitive manner, okay, without resorting to any complicated mathematics. Is that so? But for that, I need the result from the quantum theory, which is that in the quantum theory, what happens is that these punctures correspond to quanta of area. Okay, and we will see that this is, in a very precise sense, this is true. So when you look at these when you look at this flux observable and ask how does it act on your states, which I haven't defined yet, which are graph states, what you will find is that associated with each puncture, one can write down the eigenvalue associated with the Casimir of this of this operator. So right now here, this operator, this flux operator only has one copy of E. We can also define an operator which contains two copies of E. That operator corresponds to this expression, which is the area of a two surface. Okay. Now, where H is the determinant of the metric of the two-dimensional surface, right? So if you integrate the determinant over the surface, you get the area. And now the determinant, the square root of the determinant is, so you remember that root H goes like, or I should say determinant of H goes as determinant of E squared. Right? This is the relationship between the determinant of the metric and the triad or the tetrad corresponding to that metric. So this is true for the code for these densitized triads and also for the regular triads. Okay. So if you ask what is this determinant of this metric H, it goes as the determinant of these densitized co-triads. Okay, but now you're looking at a two-dimensional surface, right? And now when you calculate this determinant, you are actually calculating the determinant of a dyad, not a triad. You're calculating the determinant of two vectors of which are living on the surface. And this looks like so you get two copies of E. Okay. Later on, I will make all this much more mathematically precise. These two copies of E, again, when I go to the quantum theory, they can be written as two derivations with respect to the connection. When you take this kind of E square and you act on the states, again, I haven't defined those states yet, but I will, on these graph states or the cylindrical states, what you find is that you get something like tau square psi A, where this tau square is the Casimir of SU2. Okay, so this tau square is just like L square. It's tau x square, tau y square, tau z square. Or if you prefer, sigma x square, sigma y square, sigma z square. Right? It's like L square. So the eigenvalues of this operator, of this L square operator, are well known, right? They go as j times j plus 1. So when you look in the quantum theory, and you can define this area operator, and this area operator associates with each puncture, right, a single quantum of area. Now, so it makes sense that if you don't have any puncture, right, you don't get any area, you don't get any quantum. And if you have a puncture, you get a quantum, right? So in the quantum picture, there is no issue with this kind of a discontinuity, right? It's when you think about this curve classically, that you can, think about a curve which is almost tangential to the surface, but not quite, right? But if you think about it quantum mechanically, in the quantum mechanical picture, you can either create a puncture or not, right? So again, I guess the analogy that I would think of is like orbitals, electron orbitals, right? In the classical theory, one can have orbitals which are at arbitrary radii, right? But in the quantum theory, you only have, you have these forbidden zones. You have orbitals which are fixed radii. So there is a discontinuity there, right? And we don't have any problem with such a discontinuity, right? We call that quantum theory. So I don't know whether this is a satisfactory explanation. I think many people would not find it satisfactory. For me personally, I take it to be sufficient justification to say that yes, if these loops lie parallel to the surface, the Poisson bracket will be zero. Because in the quantum theory, such loops will not create any excitations on the surface.
Well,
I don't know whether that is good enough.
I have a naive related question.
Yeah, please. My answers are also all very naive. So
yeah, if two punctures are close enough, then
yes.
Does it cause any problem? Like in quantum
Right.
field, we have
No,
natural.
absolutely. So this is right. So this is a great question, and but this is related to the question of, well, what happens? How do you build up space-time from quantum geometry? Right. So if you take a surface, it will have if you think of the area of a complete surface of a which consists of many punctures, then to write down the area of the surface, you would have to construct the Hilbert space of all the punctures taken together collectively. And then, so as far as the notion of closeness of two punctures is concerned, right? If you're talking about a notion of separation, so you have a surface, and so then you need a concept of a metric on this two-dimensional surface, right? To have a notion of closeness of these punctures, but you don't have such a notion. Instead, what you have is a notion of adjacency, and I think that's the best you can do. Are two punctures adjacent to each other or not? Because you see, a metric is determined. A surface has a metric if it has some area. Right? If you say that a surface it doesn't have any punctures, then that surface, right? You can always define a surface with a vanishing metric. Right? A surface is just a topological space. The area of a surface is something that comes about when you endow that surface with a metric structure, right? So seen from the quantum perspective, when you have a puncture, it creates a quantum of area. It creates an excitation of your metric. So when you have another puncture on the same, and you say that that puncture is on the same surface, then you can't really define a notion of distance between these two punctures in isolation. You either have to have a sort of a mean field approach where you treat the surface as already being in a state of finite area. It already has lots of punctures, okay, and that gives you an approximate notion of a metric on the surface, right? So basically I have a tiling or a tessellation of my surface with these quanta. If I have such a tessellation, then I can define a notion of distance between one tile and another tile. right? Let's say I have a surface, I have some tessellation of this surface. Then I can define a notion of distance between these tiles, right? In some way which counts the number of steps I need to move to get from one tile to another tile, right? And there can be more than one such path. So I take some, definition which involves extremizing over all such paths. But in the absence of any such tessellation, if you just think of two patches, two quanta of area on a surface, then I really don't have any way to define a path which connects these two, right? A unique path in any way, I can't think of it, right? I can only define adjacency. But not a metric. So to define the notion of distance between punctures, I first need to have a sort of a semi-classical state, right? And when I have this tessellation, I am endowing the surface with a metric. Does this make any sense to you?
Well, let me see. Well,
there are other people in the who are listening. Does this make sense to you all? I don't know. There's one, Deva. Mustafa. One of my gauges for whether I'm saying something sensible is to look at Mustafa's expressions. So if I see like something like, yes, then I feel okay. But if I see Mustafa like concentrating deeply, then I start to think maybe I'm not saying something which is sufficiently sensible. So what about you guys? Do you have any opinions, or are you at this point like completely lost?
Well, with the explanation, do you mean this method is UV complete?
Right. So I mean, here the UV structure is given by the quanta of geometry itself, right? I mean, you don't have anything beyond that.
I see.
Right. So you are saying, well, this is the UV theory, right? Whatever these quanta of area are, you can't go any smaller than this. And there are also corresponding quanta of volumes, and you can't go any smaller than those quanta of volumes.
Okay, I'm convincing myself to some extent.
Yeah, I mean, see, I struggled for many years myself. I struggled for many years with several of these notions in loop quantum gravity. As in, like, if you have a surface and it has a puncture, that puncture gives you an area, and that was very weird to me because I used to always think, well, surfaces have area. When I think of a surface, I think of something which has area, right? But then, like, it takes some time for you to realize that intuition is not correct, because a surface is a set of, I mean, mathematically, you can think of it as a topological space, but there is no notion of distance on this topological space. There is only a notion of adjacency, and there's a notion of neighborhood and of belonging in the set or out or not in a set, right? That if you have two regions of a surface, whether if you have 2 points, whether or two open subsets, do these subsets intersect or do they not intersect, right? But I don't have a notion of some metric or which can allow me to measure distances between points. So if I want to have a metric, I need to put a metric. So at an abstract level, a surface is just a topological space. It's a collection of points, which satisfies the axioms of a topological space that that you can construct some finite number of open sets, subsets, whose union will give you the whole set, and so on and so forth. Right? So the metric only comes, so the distance, notion of a distance only comes about once I put a metric. Without a metric, I don't have anything. Right? So then what is the quantum picture telling me? The loop quantum picture is telling me that, well, the metric is coming, metric excitations are coming when I have punctures. So if I don't have a puncture, I don't have any metric. And this can seem very non-intuitive when you first encounter it, but over time it becomes very natural. I really mean that, like, because you start to realize, well, then, I mean, when I say area of a surface, well, area with respect to what? Right? Or when I say volume of something, volume with respect to what? And then you start to realize, well, volume with respect to these states of quantum geometry, which are defined on graphs. And what's the point? Right. And so if you do want a notion of distance between, like you said, between two punctures, you first need to endow the surface with a metric. How do you do that? In the simplest case, you do that by putting a number of punctures on the surface, by creating a tessellation, a tiling of that surface. Right? So that gives you a discrete approximation to a metric. Then you can ask, what is the distance between points or elements of this tile? Right? But before that, you don't have that. You don't have such a possibility. Another aspect of this quantum geometric picture is that what happens is that the action of these flux operators in different directions, they don't commute with each other. So geometry becomes non-commutative. Right? So if you can't any longer, like, say that if I have some three-dimensional surface, right, you can't independently specify the area of all 6 surfaces, for example. Or if you have a tetrahedron with 4 surfaces, you can't independently specify the area of all 4 surfaces, right? Because those operators will not commute with each other. We will see that again explicitly, maybe in the next lecture or the one after that. Okay, so a topological surface, so a surface is a topological space without any metric structure, right? So these are open subsets. Only adjacency, exclusion, and inclusion are defined. There is no concept of a distance.
So the space of so the space of gamma and S are not even manifold.
The
Right.
space of what?
The space S and gamma belong to not manifold yet. Rather topological.
You're saying this surface which is with an intersection.
Yeah. The
Yeah,
space,
this will not be a manifold. Yeah, definitely in the usual sense of being something which has a differentiable structure. Right. So a manifold would be obtained as an approximation. So a continuous manifold would be when you have lots and lots of punctures, right? So it would be like a gas of punctures living on a surface. So in that case, you would have an approximation to a continuous manifold. But that would again be an approximation. And I find that very satisfying. Personally, because I have always been bothered by the continuum hypothesis. Like, it has never made any sense to me. The continuum hypothesis says that if you have any two real numbers, between those two numbers, you have another real number. And it never made any sense to me, because it was like, how can you squeeze an infinite amount of information into arbitrarily small space? Right? It's like saying that if you zoom in on space-time, you can keep zooming in without limit, right? So, and now, of course, we have the result from holography and the Bekenstein-Hawking entropy of a black hole, and the holographic conjecture and ADS-CFT and all of these things, which tell us that, well, yeah, space-time has finite number of degrees of freedom. Any region of space-time has a finite number of degrees of freedom. That is what Bekenstein-Hawking tells us, right? That any given region cannot have more degrees of freedom than the area of a Schwarzschild black hole, within which that region can be contained. So, and in the LQG picture, that area has a very beautiful and very natural interpretation. It comes about because you have this surface. Again, remember, a surface is an abstract thing, and there is a graph which corresponds to your state of geometry. And I won't draw I'll draw some of them maybe. There is some internal structure that it has here, but that is not so important. What matters is the configuration of punctures on the surface. So the area of the surface is measured by looking at all of these punctures, right? And in the first approximation, one can assume that the area is simply an additive function of these punctures. That means you don't have to worry about entanglement between these punctures and so on and so forth. That the area eigenvalues just add, right? So if you have an area A1 here and an area A2 here, then the area of the whole surface of this is A1 plus A2. You don't have to worry about any interference, so to speak. So in that case, the area of the whole horizon can be written as a sum of the areas of all the punctures taken individually. And strangely enough, or maybe not so strangely enough, this is sufficient to give us the Bekenstein-Hawking entropy up to some factor, which is a matter of a lot of debate. And gamma is something called the image Z parameter. So this is the entropy of a black hole and a short shell black hole, right? And it's not an external black hole, and you can calculate it exactly in loop quantum gravity. And you can't do that in string theory. Even now, you can't do that, right? And it has been more than 20 years since the first claimed calculations of black hole entropy in string theory. But those calculations apply for certain extremal states of black holes. Now, it's possible that most black holes in nature might turn out to be in those extremal states. Well and good. But if you consider a black hole by itself in the absence of any matter to feed it, then we know that over time, gravitational radiation will carry away all the rotational angular momentum, and you'll be left with a static object with maybe with some finite rotation, but most likely with no rotation. And that would have an entropy given by this expression. The one shortcoming in the loop quantum gravity approach is that we don't have a nice way to understand non-rotating objects, rotating black holes. But I think that is something that is very close to being accomplished. It just requires a little bit of change of in loop quantum gravity also there are certain dogmas that have developed. So you have to shed those dogmas from time to time. So I will, stop here because I mean, we've been going for an hour and a half, and I think that's long enough. Okay. But of course, this discussion, the whole best thing about this is the discussion aspect of things. So yeah, please, whatever questions that you have. And like I said, there have been a lot of guesses and a lot of, intuitive decisions made along the way. So, for instance, this decision that, well, you should construct this quantum space based on this kind of a smearing. I mean, this is a choice, right? This is not dictated by any universal principle. It is a choice. It happens to lead us to nice results, like the ability to write down an area operator or a volume operator, right? Now, those results could also be completely illusory. They could be illusions, just like in string theory, you end up with results that are illusory. All right. So ultimately, they have to be compared to experiment, and finally, we are reaching a stage where one might be able to do that in the laboratory, and even in certain astronomical observations. Yeah, Mustafa.
Yep. I have a very naive question, and that is, where are we using Chern, the Lagrangian that we wrote down at the very beginning, the Chern-Simons
we are
Lagrangian?
Not. We are not.
Okay.
We are not.
Okay.
I just wanted to give you an illustration of how, in this formalism, you can solve the Hamiltonian constraint exactly without making any assumption about the symmetries of the spacetime.
Okay, so again, we had the Hamiltonian constraint from before. It's something that we looked at in the last lecture. Then we defined this new state called the Kodama state, and we looked at solutions of it, right? That's right. And so my question is, where have we used that Lagrangian at all? Was it just a demonstration that? Yeah,
it was just a demonstration.
Okay, perfect.
Now the question is that how can you connect that to real cosmologies? Like I said, I mentioned some references that one can go and look at. papers by including Kodama, then Smolin, then Chopin-Su and Randono. And I don't know, there might have been more recent work I'm not aware of. But I think it kind of died off because it was not clear to people how to construct a geometry out of this. Like you can construct a state, but what is the space-time interpretation of this state? Right, so it's a demonstration, but even that demonstration is for the first time, right? It's possible. Like with the Wheeler-DeWitt equation, you don't have any solutions. You don't even know how to write down the constraint in the most general case, right? So in that sense, it was a huge leap from what was known previously. Okay. Anything else?
Why the loop quantization needed rather than Wilson line?
No, so we are working with Wilson lines only, right? These are Wilson lines.
But so in the loop quantization,
right?
Does it mean we deal with Wilson loop rather than Wilson line?
Yeah. Well, we deal with Wilson lines and Wilson loops.
Oh, okay.
But yeah, I mean, it's all those are the basic because if you want to define a gauge invariant state, then you have to use something like a Wilson loop, right? And just on a interesting historical note, if you happen to read Witten's papers from back in late 1980s, where he is, for instance, talking about 2+1 dimensional gravity as an exactly solvable system, and an updated version of that paper in 2006, he repeatedly references Ashtekar's work. He is very well aware of it. And he says that, well, he, for example, in his 1989 paper, he's showing that 2+1 dimensional gravity can be written exactly as a gauge theory, which is Chern-Simons theory, actually. And that it's equivalent to Einstein gravity in 2+1 dimension. So in 2+1 dimension, Einstein gravity does become equivalent to a gauge theory. Then he says that, well, in 4 dimensions, that's not the case, right? Though, then he mentions Ashtekar's work. And then again in 2006, he mentions that, well, this is the starting point of loop quantum gravity. So it's not as if the, the leaders of the string theory community don't know what loop quantum gravity is. They're not aware of its existence. They know very well. But none of them have. But this year there was actually a massive shift in that. There was a massive sociological shift because we had this conference in July called Quantum Gravity 2020, and in that conference, I believe not for the first time, but after a gap of many years, that people like Strominger and Witten and others, they participated along with Ashtekar and other people and Rovelli and Smolin. And in this meeting, Strominger said something very, very interesting. He said, he was typing in the Zoom chat, and he said in one of the sessions, he said in the Zoom chat, I took the screenshot for evidence that he's not even sure if string theory is the right field. And that was a shocking statement coming from Andrew Strominger, right? He's one of the people who is associated deeply with the development of string theory. So in string theory land, all is not well. They realize very well that there are problems with their theory, but there is still a very strong reluctance to admit that, well, maybe loop quantum gravity might have something to teach us. This is like a ego thing, or I don't know what it is, but it's there. And so yeah, anyway, I'll stop my editorial pontification. Okay, so I'll see you guys again on Wednesday, where we will talk more about this quantum theory and continue onwards to explore unknown vistas. Okay. All right. So once again, Merry Christmas to all of you, and see you on Wednesday.